In part 2 of multiplying and dividing radical expressions, we're going to talk about the dividing aspect. And this property written at the top of the screen is one we've run across already, except we've pretty much worked this direction. If you have a fraction under a radical, you can separate it into two separate radicals, and the other direction is also true. We used this symbol in class that said that the definition goes both directions. So in this problem, we want to find the simplest form of each quotient. Remember, quotient is division. The square root of 18x to the fifth over the square root of 2x to the third. The best way to deal with this problem is to first write this whole entire fraction under one radical. And the reason we're going to do that is because now that fraction can be reduced. 18 over 2 is 9. And x to the fifth over x to the third is x squared. That's the property where you subtract the exponents. Well, now that I've done that, 9x squared, that's 9 times 9 times x times x. A square root says circle the pairs. Well, I can take out a group of 9s and a group of x's, so the answer must be 9x. So a lot of times going about the process of simplifying before you do the radical is going to help us out with the problem. Let's do that again with this problem, the cube root of 162y to the fifth over the cube root of 3y squared. I'm going to start by putting the whole entire fraction under one radical. And then I'm going to simplify because 162 divided by 3 is 54. Oops. And y squared, or y to the fifth over y squared, is y to the third. So now, 54, you can break it down using prime factorization, or you can find the largest perfect cube that divides into 54, whichever one you want. I'll go and do this. It's even, so I can break it down into 2 and 27, which breaks down into 3 and 9, which breaks down into 3 and 3. So we're going to do the cubed root of 2 times 3 times 3 times 3, and then there are 3 y's. Cubed root says look for groups of 3. I can take out one group of 3's and a group of y's, and I'm left with a 2 under the cube root symbol. So it must simplify into 3y, the cubed root of 2. Now, we don't like to leave radicals in denominators. These previous two problems we did, the radical went away. But sometimes it doesn't. And so we're going to do this. I'm going to start you off with a simplistic problem, like 1 divided by the square root of 2. Well, to get rid of the square root of 2 that's in the denominator, it would be nice if the number under the radical was a perfect square. Well, the closest perfect square to 2 is 4. So maybe if I multiplied this by another square root of 2, I could get rid of the square root of the denominator. But when you multiply one part of a fraction by something, you have to multiply the whole entire fraction by something. Because really what you're doing is you're multiplying by 1. Remember that anything divided by itself is 1. And what happens when you multiply anything in the world by 1? Nothing. Now, the fraction may look different, but its numerical decimal value would be exactly the same. So now I would get the square root of 2 divided by the square root of 4. Hey, the square root of 4, that's just 2. And this is called rationalizing the denominator. And this is actually a really good fraction to think about because it's one that's going to pop up when we study trigonometry. And oh, will it pop up all the time. All right, now let's talk about rationalizing the denominator in something that's a little bit nastier, like the cube root of 5x squared over 12y squared z. The first thing that I want you to realize is that the fraction that's underneath the radical can't be reduced. There is nothing to simplify. So what I'm going to do is I'm going to start this one by rewriting it as the cube root of 5x squared over the cube root of 12y squared z. Now, to get rid of the denominator, I need everything underneath the radical to be a cube of something. So to help me out, I'm going to simplify or break down using prime factorization everything in the radicand of the denominator. So 12 is 2 times 2 times 3, and then I have two y's and a z. Okay, I need 3 of everything. I need 3 2's, but I'm missing a 2, aren't I? I have 1 3. In order to have 3 of them, I need 2 more. I have 1 y, so I need, I have 2 y's, so I need 1 more y. And I have 1 z, so I need 2 more z's. That's how I'm going to determine what I'm going to multiply by, is by figuring out what more factors I need, so that when I multiply the two together, I have 3 of everything. Alright, so this simplifies into the cube root of, let's see, I shouldn't do that. That simplifies into the cube root of 2 times 3 is 6 times 3 is 18 yz squared. So I'm going to multiply 12y squared z, the cube root of, by the cube root of 18 yz squared. When I do that, though, I have to multiply by this because I want to multiply by 1 in order to have this, in order to get the same fraction of equivalent value. So now the properties of radicals say I can multiply straight across. So I get the cube root of 18 times 5 is 90. I have x squared, y, z squared. And in the denominator, I'm going to end up with the cube root of 216 y to the third, z to the third. Well, now that's something, the denominator is something that can be simplified. The cube root of 216 is 6. The cube root of y cubed is y, and the cube root of z cubed is z. And then nothing happens in the numerator. I'm just going to leave the answer like this. That's called rationalizing the denominator. So what we did was we went back and we tried to find what we could multiply the denominator by so that I had 3 of every factor. Because if I have 3 of every factor, when I take the cubed root, then I'll know the solution. Once I figured out what I had missing, I multiplied it all back together to find out what I was going to multiply my original fraction by. Remember that you're multiplying the original fraction by 1. Once I multiplied them together, then the denominator was ready to simplify into something that had no radicals. And this is called rationalizing the denominator. Let's try that one more time just for posterity. Let's rationalize or simplify the cube root of 3y over 20y squared. Well, first of all, if there's anything in the fraction that can be simplified, I want to do that. And it turns out that I can simplify these y's. I get 3 over 20y. Well, now I'm going to rewrite as the cube root of 3 over the cube root of 20y. In order to determine what I need to multiply my denominator by, I'm going to use prime factorization to break this down. The denominator is the cube root of 2 times 2 times 5 times y. So I'm going to need to multiply by, I need another 2. I'm missing 2 5's, and I need 2 y's. Well, 2 times 5 is 50 y squared. So in order to rationalize the denominator, I'm going to have to multiply the numerator and denominator by 50y squared. Now I can multiply straight across. I get the cube root of 150y squared all over the cubed root of 1000 y to the third. Well, 1000 y to the third simplifies into 10y. And you have the cube root of 150y squared on top. And now you have no radicals in the denominator. This is called rationalizing the denominator.